So think about this for a second. What do artificial intelligence, cancer vaccines, superconductivity, fusion energy, and supermassive black holes all have in common? I mean, it sounds like the setup to a massive sci-fi joke, right? But the answer is that every single one of these massively diverse fields is experiencing a paradigm-shifting breakthrough right now. We're talking about discoveries that are actively shattering the boundaries of what we previously thought was possible.
Welcome to our latest deep dive. Today, we're going to take a structured journey outward. We'll start from the completely intangible and microscopic, and step by step, we're going to zoom all the way out to the absolute edge of the observable universe. We are going to see exactly how today's science is rewriting our reality across literally every conceivable scale. Here is our roadmap for today. We'll move systematically through 5 distinct scales. First, AI learning to self-verify. Second, mRNA technology defeating cancer resistance. Third, a huge new record in superconductivity. Fourth, the ITR fusion ecosystem. And finally, the James Webb Space Telescope's mysterious little red dots. Let's get right into it.
Section 1. The digital realm, where AI learns to self-verify.
So we hear about artificial intelligence constantly, but we're now hitting this critical threshold where AI is independently evolving its own logic. Recent research is showing us something absolutely fascinating. Language models are actually becoming significantly better reasoners simply by learning to self-verify their own outputs. Instead of just guessing the next word, these models are essentially double-checking their own logical pathways. It's like they're proofreading their own thoughts. By verifying their own work, their capacity for complex reasoning just jumps dramatically. It means fewer hallucinations and a profound shift from an AI that just mimics human speech to an AI that can actually evaluate what's true.
Moving on to Section 2, the microscopic scale where mRNA defeats cancer resistance.
To see how this builds into our physical world, let's step up to the cellular level. We're seeing how the exact same mRNA technology behind our COVID-19 vaccines is being repurposed for a completely new battle against cancer. To really get how this works, we kind of need to understand the difference between cold and hot tumors. Cold tumors are basically in stealth mode. They completely evade your body's immune system. Hot tumors, on the other hand, trigger inflammation, which makes them highly visible so your immune defenses can actually attack them. You can think of this new mRNA therapy as a biological thermostat. It essentially turns up the heat on those cold tumors so your immune system can spot the cancer and strike.
So how exactly does this thermostat work? Well, a groundbreaking study out of MD Anderson just mapped out this brilliant 3-step sequence. First, a standard SARS-CoV-2 mRNA vaccine is introduced. Second, that triggers a massive surge of a specific protein called type 1 interferon. And third, this response forcibly turns the tumor hot. The study found that if you do this within 100 days of starting immune checkpoint blockade therapy, it dramatically improves overall survival rates, all because the cancer suddenly becomes exquisitely sensitive to the treatment.
Now, the actual mechanism here is what's truly mind-blowing. The lipid nanoparticle carrier, the LNP that protects the mRNA, isn't just a delivery truck. It acts as a powerful immune booster all on its own. Together, the RNA and the LNP trigger this systemic interferon response that literally rips away the cancer's camouflage. It's an off-the-shelf strategy that completely reshapes the tumor's microenvironment, and it proves that immune therapies don't always have to rely on super-customized, patient-specific antigens.
All right, zooming out to Section 3, the infrastructure scale, breaking the superconductivity record. So, from microscopic cells, we move to the human infrastructure scale. Down in Texas, physicists at the University of Houston just broke a massive, century-old barrier. They hit 151 Kelvin, which is about minus 122 degrees Celsius. Now that might sound freezing to us, but in physics, that is a massive new ambient pressure superconductivity record. It's the highest transition temperature we've achieved without needing extreme high pressure since superconductivity was first discovered way back in 1911. Achieving zero electrical resistance at higher temperatures has literally been the holy grail for scientists for over a century. And how they pulled this off is just a masterclass in material science. The old way required keeping materials under this constant, crushing pressure, which is totally impractical for real-world use. But their new method uses a technique called pressure quenching. It's actually a lot like how artificial diamonds are made. You apply intense pressure, cool the material down, and then rapidly release the pressure. This effectively locks in those enhanced superconducting properties so the material stays stable right out in normal room air.
So why does this matter for you and me? Well, right now, just sending electricity through our standard power grids wastes about 8% of the power due to resistance.
If we can build a frictionless highway for electricity using ambient pressure superconductors, we wipe out that 8% loss completely. We're talking about saving billions of dollars globally and drastically cutting our environmental footprint simply by not wasting the energy we're already producing. Next up, Section 4, the planetary scale, looking at the ITER fusion ecosystem.
From energy grids, let's move up to a machine designed to mimic the very energy source that powers the stars. The massive international ITER project in France is actively accelerating under a highly realistic schedule known as the Baseline 2024 plan. They've successfully completed all of their giant superconducting magnets. Their tungsten plasma-facing components are now in series production, and large plant systems, like their crazy cryogenic infrastructure, are actively operating. After years of construction, they are officially moving into integrated commissioning.
But why go to all this unbelievable effort? It really comes down to one crucial metric, a Q factor greater than or equal to 10. You see, ITER isn't just a science experiment to see if fusion works. It's a stepping stone built specifically to hit this massive energy gain. A Q of 10 means the plasma produces 10 times the energy that was pumped into it to spark the reaction. If they can prove this at an industrial scale, fusion suddenly becomes a totally realistic, everyday baseload power source for humanity.
Finally, Section 5, the cosmic scale, JWST's little red dots.
Let's zoom all the way out from our planet to the absolute edge of the observable universe. The James Webb Space Telescope is finding things that are seriously challenging our standard cosmological models. It's uncovered this abundant and highly debated new population of high redshift objects, affectionately called little red dots, or LRDs, which, honestly, is a pretty ironic name considering the immense cosmic forces likely going on inside them. These objects have a really unique V-shaped signature. They emit blue ultraviolet light, but are dominated by very red optical light, and they look like incredibly compact dots, roughly within the first billion years after the Big Bang.
Because these objects are just so weird, scientists have been fiercely debating what they actually are. Theory 1 suggests they're incredibly dense, compact, star-forming regions. If that's true, we're looking at the highest stellar densities ever observed. But Theory 2 argues they are active galactic nuclei, basically supermassive black holes that grew way, way faster than our current physics models say they should have.
And the latest evidence is brilliantly settling this debate. When we look at the diagnostic data and the multi-epoch observations of specific targets, we see clear variability in their broad spectral lines, specifically H-alpha and H-beta, over just a few years. Star-forming regions just do not fluctuate like that. That kind of rapid variation requires insane gas velocities, which is basically the smoking gun, proving that these little red dots are actually actively feeding overly massive black holes.
Section 6, Conclusion, the connected future.
Okay, let's take a breath and step back. From the edge of the early universe down to the AI in our computers and the cells in our bodies, human knowledge is exploding outward across every conceivable scale simultaneously. So I'll leave you with this. Which of these leaps, from self-verifying AI to cancer-fighting vaccines to ambient superconductors to the infinite promise of fusion, do you think is going to most profoundly reshape our world over the next 10 years? Thanks for joining me on this deep dive, and as always, keep questioning the universe around you.